So this is what's often called abstract algebra or modern algebra. Same thing. Meaning, well, the abstract is, I hope, clear. It is we're trying to do algebra, but without describing with what exactly. So how matters, not what. So are they numbers or not? We don't know. We don't care, right? So this is just a good example of where you could start doing algebra, but that's still not abstract because we have a specific elements of that set. It is the equivalence classes of numbers under congruence. This specifically division by 2. Okay, so even and odd. So the specific sets that we're dealing with, and we add them in that manner. Okay, but it is the step in the right direction because we're now getting these properties not necessarily associated with the with numbers as we know them anymore. Okay, so they're applicable in a situation which is quite a lot different. So even though it still comes from numbers, but the algebra we do is not with numbers anymore. Okay, these are not numbers; these are sets of numbers. Okay, so then the idea was then to write out the 4 main properties of such algebra. So we have associativity, commutativity, the zero element, the negative element. Then the claim is that this is sufficient in order to do any algebra freely, just as we do with the regular algebra. Okay, so that cannot be proven mathematically, but certainly you can demonstrate certain things. For example, you know how to subtract. Okay, you add the negative element of x. That's meaning subtraction of x. So even though we start with nothing but addition, but that's kind of having that extra element. Negative x is in fact allows it to add. And then secondly, for example, we can also do cancellation. So that's we have already two ideas from algebra, even though not limited specifically to not limited to these 4 basic axioms. It gives us more. Okay, so we want to limit to the 4 axioms so that as few as possible. So that's the idea. So there are many algebra tricks that you can think of. Well, I don't know. Well, I don't want to talk about things like FOIL because we're still doing addition only. We're not doing any multiplication for now. But once again, we just limit it to a bare minimum number of axioms. So it's easy to keep track of things. And then you derive everything else, such as, for example, cancellation property. It is in fact might be then a theorem. So a plus b is equal to well, how should I put it? Cancellation property is a plus x is equal to b plus x, means that a is equal to b. A is equal to b. Okay, so that is a theorem then. And that theorem can, as well as the rest of them, can be proven in the abstract. So without referring to the nature of the elements we're dealing with, all we know is the axioms and that operation on. So we have set, and we have a binary operation on it, which satisfy those properties, 4 properties. Okay, so this is still informal because what is that? What is the meaning of operation? Okay, so that has not been explained with the. And all those pluses and minuses are just put in between the numbers, or they're put in between some sets if we're doing abstract, if we're doing Z2 or Z3 or Z4. But it is in fact, there's a precise definition here. So definition, a binary operation first. So given a set, x, a binary operation on x is a function. So everything can be explained with sets and functions on sets. Say, well, let's put f there, it doesn't matter. X, and this is the Cartesian product comes into play very conveniently. So as you can see, there are no numbers. there's only set. And how do we do operation, binary operation? Well, they just the function. So any two elements. How do you pick two elements in the set X? You create a pair X, Y. So if we need notation now, then this is, we have a pair X, Y, both elements of X, Y, and then they correspond to, under this function, where does it go? It goes to f of x, y naturally, but the notation that we use, so to emphasize the nature of this operation, is say x star y, or it could be x plus y, x dot y, or sometimes simply x, y, depending on what you prefer, depending on the circumstances. But it doesn't matter. It doesn't matter. This is purely notation. Depending on the circumstances, different notation is used. Star especially is popular to emphasize that to make sure that you will not follow your intuition too far. So you are dealing with numbers, and you are not really, and then you put the number plus between them, and you want to think about it as you have always been thinking about it as addition, but maybe it is now it is something else, and we haven't decided what it is. It is abstract. So that's why star helps. So that's what you do in modern algebra, and then you can define a group. So given a set X with a binary operation, let's say it's star, okay. The pair X star is called a group. If axioms, which axioms? Not all the axioms. I'm skipping commutativity, so it is 1, 3, and 4. 1, 3, and 4 are satisfied. If number 2 is also satisfied, it's called an abelian group. In other words, if we add commutativity. Initially, groups were thought about the commutative groups with commutativity property. So group, abelian group. So let's quickly go through examples of what we have or have not seen of groups. So examples are, the one that we started with is Z. Usually you don't just say Z, even though it is presumed, but you put an operation that to specify what that operation is. Well, maybe let me write those properties one more time, so that with using stars. Okay, so number 1 is associativity. So the star, what the meaning of the star is irrelevant. Okay, number 2, commutativity. If the condition is satisfied, then that's all it takes. A star B is equal to B star A. Number 3 is the 0. So there is 0 in X, such that 0 star A is equal to A for all A in X. Okay. Number 4, the negative element. For any, you gotta either use quantifiers or not use quantifiers. So let's say no quantifiers. So for any A in X, there is negative A in X, such that A plus negative A is equal to 0. Okay. So these are the four axioms. They are written with operations now denoted star, so that it could be multiplication, it could be addition, as we have seen, but in a different circumstance it will be multiplication or something entirely different. We're going to see a couple of examples. So starting with the simple one, as I said, z with addition. Okay, so it is a group. It is a abelian group, an abelian group, and as we have seen before. But so with the obvious operations of 0 means number 0, negative means negative number. Okay, but that also just around the corner there are more of the same. How about we take the real numbers? It's the same thing. So it's the numbers are the same. There are just more of them, and the operations are the same. And in fact, if anything, you go like in this direction. So you do the real numbers first, and then you show that it's a group, and then then it is the question becomes to demonstrate that Z is a group. Why? Because at least there is an issue of what to demonstrate that our binary operation is well defined. That is a big problem. Frequently, if you want to see a group somewhere, you might not recognize that the problem is there might be the binary operation is undefined. So you have to say, if I am doing an operation that I have specified, I have to produce a new element of the same set. So in particular, I have to explain why this is a group. Number one to do is that integer plus integer is an integer. You don't have to worry about that if you're dealing with real numbers. Obviously, or it is more obvious that the outcome will be still a real number. And then the operations. So as we know, these operations to be satisfied for the arithmetic that we know. So we're fine with this. But you can take it further. How about rational numbers? Is it a group? Well, remember, once again, it is the rational numbers are real to begin with. So if we postulate that this is a group, based on pretty much our experience, what we know about numbers of algebra of real numbers, then addition of real numbers, period, then we can also say that the operation would make sense for integers or the rational numbers. The question once again becomes, does the operation make sense in the first place? Does it? On the rational numbers? Addition of rational numbers, does it make sense? Yeah. In what sense does it make sense?
So you can add two numbers together and get another rational number.
That's right. Two rational numbers added together give you rational numbers. So x, y belongs to q, then x plus y belongs to q. That works out. Anything else you can suggest along these lines? Anything bigger than real numbers?
Real numbers squared?
You mean this? Yes. So yeah, vectors. Maybe you have. Well, so you've seen vectors, right, in Calculus 3, and you know vector algebra. Okay, so that's a perfectly good example, as a matter of fact. So once again, addition, subtraction. So 0 stands for the 0 vector. Negative means you multiply a vector by negative sign. Everything works out perfectly. So great. So bigger. Actually, the example that I was thinking before thinking about vectors are 2 or 3 or beyond. That doesn't really matter. Example more subtle is, well, not by far, is the complex numbers. Okay, also once again, Adding two complex numbers, still a complex number. Okay, so bigger is easier to make it bigger because you go from Z to Q to R to C, and then you can also look at vectors, either real vectors or you can have complex vectors too, by the way. So that all works out. All of these are groups. Okay, so the only thing that for us to worry about once we understand the algebra is that it is we do not, when we carry out those operations, it does not takes us outside of that set. Okay, so add two vectors, you still have a vector. In fact, how about z2 z squared rather is also a possibility. So in other words, remember integer valued vectors, right? So once again, you can add them if both the coordinates are components of the vector are integers. You add them together, you still have it. Okay. A smaller. Now it's a tricky. Can we go smaller than z? Smaller than z. How about the natural numbers? Is it a group? Are you sure?
You can add any two natural
Yes.
numbers together.
Okay.
Another natural number, right?
Yes. What about axioms? Well, you can include zero. Sometimes natural numbers include, depending on the person, include zero, not include zero. So you can include zero if you want to. So let's starting with zero. So I mean, that is our choice on this circumstances. So it will be 0, 1, 2, 3.
But no negative.
There is no negative. So no. The answer is no. No negative. So not a group. So it's in fact easy to make up sets that with operations, the subsets of Z, and they won't be groups. So I don't know. Well, actually, let's take a look at this. Two examples, number 1 and number 2. Even numbers and odd numbers. That's not what we have been talking about just yesterday about the modular 2 addition. No, I'm talking within. The set X is the even numbers, or set X is the odd numbers. Are these groups? They are subsets of Z, right? So which means that the operation that we can think of are there already given. So we're not trying to invent anything new operations. We will do that in a minute. So are these groups?
Odd wouldn't, because if you add two together, you don't get the same thing.
That's right. So 1 plus 1 is equal to 2 and does not belong to X. Okay, so no. What about even? Yes. As a matter of fact, yes. Well, you can verify first of all the two even, add up to even. That's to begin with. Then you look at the axioms. And you realize that all the operations, associativity and commutativity is still satisfied, right? Because they are satisfied for the real numbers. The only thing to worry about is the zero and the negative element. Unfortunately, that works out zero. The best thing about that zero is an even number, so we were good here. And the negative over negative, the negative over an even number is an even number. Okay. The main problem with odd numbers turns out that even though they seem so symmetric, but really it doesn't work out. They don't contain zero. Zero is not an odd number. Okay. So as you can see, we can make up many examples of non-groups because they're closed, not closed as that expression you will see, not closed under the operation. So it takes you outside of the set by carrying out operations. And that's not allowed, or some of the axioms fail. Primarily, it would be what were the last two. So then that's how we went on. So these are kind of examples up to now. You've seen it in calculus. Outside of what takes us outside of calculus is Zn. Okay, so integers modular n. Okay, so that's what we're going to study extensively, and we need to demonstrate that it is indeed a group. It takes a little bit of work, but you can see how different it is, well, why it's so worthwhile, how different it is from the rest of the examples, because for one it is finite. Even though it pretty much takes as the starting point the same algebra, however the set itself is finite, so it has n elements. Okay, it has n elements, so unlike all these examples, it is finite, and we have a whole bunch of them, examples for each, and there will be integers modulo n, z sub n, it will be a group. So we'll demonstrate that. All the groups that we have seen are abelian so far. So because the operations come from the algebra of real numbers as we know it, then either it is not a group, or if it is, then it is a abelian group, right? So because the R is abelian, and so every one that we make from it or in it will also be abelian. So Z and Zn, all of them will be abelian. So to think of an example that is not abelian, well, actually one more example of abelian group that I mentioned yesterday. So let me remind you once again: rotations. Just period rotations. So it's like 0 to pi. So you remember what I'm talking about. So I don't want to go into specific here, but you know that two rotations combined together give you another rotation. You just add these two numbers, except you subtract 2 pi as many times as necessary to make rotation smaller. So it is once again, in fact, another equivalence class, best understood as an equivalence class, and still abelian. Example of a non-abelian group is this. It's interesting, kind of complex, but it is right what we have seen recently, and that is bijections. So given a set, let's call it A, and let X be the set of all bijections F from X to X. Okay, nothing else, no numbers, no vectors, nothing. So we are looking for a group here. I pointed out the set, so the set of bijections. Okay? What is the operation? I mean, we want X to be a group, so we need to pick an operation. What's an operation? Well, there aren't, when in the set theory environment, there aren't too many operations that we have. What can we do with functions when there are no numbers? What?
Inverses?
Well, close. Compositions. So is the composition or compositions. So in other words, if I want to use that star, I say F star G is in fact F composition G. Okay, so that is the operation. Why this works out to begin with? Because we know that the composition of two bijections is a bijection. So indeed, it is an operation on that binary operation will be from X to X. Okay, so under this operation, you produce more bijections. Okay, so not a problem. Okay, so now let's look at the axioms.
What's the star stand for? Is that just like any?
The star, it's like a placeholder. So depending on what group you create, it might stand for anything. So it has been standing for addition, could stand for multiplication as well in the circumstances, and now this is a composition. So circle is the actual operation that we knew before, and now we define. So this is the definition, defining what's the meaning of star. Here it is, the last line. Okay, so let's look at the axioms. Axiom associativity, number one. So F composition G composition H, is it equal to F composition G composition H? Do you think it's true or false?
I would say it's false.
Really? No, it's true. Well, the composition can be, the composition is like this, right? So you carry out the composition on the left, and then the first one, the second one, so this is my F. Hold on a second, we have three of them. And all of them are bijections, so that's not a problem. And the only way to get from the beginning to the end is just follow the arrows. And the fact that you might combine the first two arrows first, and then followed by the third, or you combine the second and third first, and then add the first one, the result will be the same. So I don't want to. It might take some hard time to convince you that this is actually true, but well, maybe it doesn't have to be a set after all. This is a pretty good example, so you can actually have a better time or easier time to understanding this if you, instead of a set, you pick some, say, real numbers. So you're talking about all bijections of the real numbers, and then this idea still works out, and it's still well, whatever we're going to discover now. So commutativity, F composition G is equal to G composition F. Is composition commutative? Polishing and painting, or painting then polishing. Does it make a difference? What?
Yeah, it makes a difference.
Okay, so what's the answer? Yeah, it's false, yes. So no, so it's not commutative. Example, if you pick two examples, numerical, you pick numerical functions. If you don't want to, well, probably, if you're looking for an example, don't make it harder than it has to be. Go straight to the simplest possible situation. So, let's illustrate it with either you go to like real numbers as I suggested, but you probably can to illustrate this you can show something even more simple, as with just like elements have sets having two elements like that. So let me see. So it should be the same set. Let's say we have two elements. So that's my set X. And now we have two functions. And we want to show that they do not commute. Okay? So, well, they actually all okay. I don't think it works out with two sets. Well, let's have an example which is not necessarily bijections to begin with. That's easy. So if this is will be my F, and this is my G. Okay, right? So this is F and this is G. Now if I take the composition G then F, G then F, what do I get? Well, let me write it here. So I'm composing them, but I'm going with G and then F. So then where do the arrow go? So every goes to the second element, under G goes to the second element, and then goes to the first. So that's the result. Okay, now if I go the other way, G circle F, then first f is executed, which means that everything goes to the number 1, the first element, and then everything goes to the second element. So that's the result. Okay? So that's certainly not commutative. Okay? The example of, well, okay, I'll let you think about it at home, homework. So example of non-commutativity of bijections. These are not bijections. So this is just illustrate that compositions in general do not commute, but maybe bijections do. So, well, I'll let you think about it. So it's not commutative, but it's not all lost. So maybe it is a group. It's just not an abelian group. So number 3 is the 0. 0? What 0? There is no 0. What 0? There are no numbers here. So what are we looking for here? Look at the axiom. Number 3. There is a 0, just an element. So in other words, a bijection, such that when composed with any other bijection, we'll give that bijection again. Okay, let me write it out for you. Okay, so there is a bijection. I don't want to, well, should I call it 0? Well, let's 0. From A to A, such that for any other bijection, F, once again from A to A, we have what? 0 composition. In what order? Order actually matters. Yeah. I'm afraid I have to fix it myself here. Yeah, two conditions. Unless there is a commutativity, you have to point that out, and that applies here as well. Okay. Okay, so it's fixed now. Okay, so 0 composed with F is equal to F, and F composed with 0 is equal to F as well. What is that 0? 0, not real 0. A special function that composed with any other function gives that function itself. Does it mean anything to you? Well, maybe the 0 is not a good name, but so this is my what?
Like the double inverse? I don't know.
No, double. Yes, it is a double. You can say it is a double inverse. Yes, there's a name for it. So if you look at the definition of the inverse, the double inverse actually appears there, and what is it equal to?
So
No. Inverse of x is equal to x. That is the function I'm talking about and you're talking about. So there's a name for it. What's the name? This one. The name of this one? The function that gives you x for each x. The input is x and the output is x2. What's the name of it? So if this is my f, well, I don't think picture will actually help here. The name is the identity. Remember the identity function. So if you still want to use 0, even though it never actually happens, so the notation becomes awkward once we step away from the numbers. So the notation for the identity matrix is usually ID. So ID of x is equal to x. Or sometimes ID sub x to indicate the set. Another one is 1. Sometimes they put 1 there as an identity function as 1 because it's like multiplying by 1. And number 4, negative. So once again, if I take that thing, I will f, composition negative f is equal to identity. What is that negative f? Now, it is the inverse, finally. The inverse, that's where the inverse plays. So negative f is f inverse, because the composition gives you the identity as defined, either on one side or the other. So even without commutativity, both of the properties are satisfied by the definition of the inverse. So f inverse f of y, this is actually x, is equal to x, and this is y. Okay, so this is the definition of inverse for a bijection. Okay, so it's a function that undoes the effect of the bijection, and it is exactly what the negative element does. So if you have 5, you can undo the effect of 5 by subtracting 5. Okay, so adding 5, subtracting 5, it is in fact literally the inverse. So if one function is add 5, the other function, its inverse is subtract 5. Okay, so that's how 5 and negative 5 are actually kind of inverses of each other in that sense. Okay, so as you can see, everything works out except for commutativity, so it's a group but not an abelian group. Okay, so and that's typical when you deal with functions, and it is typical to choose the operation to be the composition, and then with composition, as it is typically the case, it's not going to be commutative, but the group structure usually is there. Okay, so I think we've had enough. What happened here? We've had enough examples. So let's now concentrate on modular arithmetic as just creating. We know what it is already. Now we just want to develop, demonstrate that it is a group. So all the algebra of modular arithmetic. So let's just review all the definitions in the results. So number 1 is the remainder theorem. The remainder theorem, remember, so what is it? X is equal to Qn plus B. So n, that number is where that we're going to be concentrating on, so that is our divisor. Okay, so fixed divisor. So for modular arithmetic, it only works within the same module, being the same divisor. So same divisor. So every x is represented when x x is fixed, n is fixed, then we can find q and b, right? So that's what the remainder theorem says to us: b between 0 and n. Okay. Q is the quotient, b is the remainder, q is the quotient, x is our number. Okay, so then we will be dealing with these numbers, and we represented all integers are represented in that fashion, in a unique way. Okay, so so all integers can be represented and uniquely in this way. Once again, for a fixed n. Okay, so that creates our z sub n. So then define z sub n. Well, let's the definition is x is congruent to y modulo n, if x and y have the same remainder when divided by n. Okay, so by the theorem that b, the remainder, is unique, so we're good. So if they have the same remainder, then we have an equivalence relation. So we have proven that it is indeed equivalence relation. So theorem proven previously. This is an equivalence relation. Okay. Notation, once again, we have seen for the congruence x equal y mod n. Okay. What else? Now, remarkable, the theorem that makes life easier is the following. The congruent, to say that they have the same remainder is a bit awkward, even to say it, and especially for actually any kind of computations, comparing those remainders is a pain. So there is an easier way. So suppose we have x equivalent to y, which means then x is equal to, say, qn plus b, and y is equal to pn plus b, right? Same remainder. Same remainder, and is fixed. X and y are equivalent if this is the case. Okay? Let's subtract. X minus y is equal to what? Q minus pn. Okay, so you can see what is the relation between x and y is now. X minus y is divisible by n. So that's much easier to handle. And then we have a theorem then. So x equivalent to y if and only if x minus y is divisible by n. Okay, so every time you're trying to prove something, that it will be much easier to do. If we write this out, so that's the theorem that we just proven. Okay, so if we write this out, then what does it look like? So x is equal to y mod n if and only if x minus y is what? Divisible by n. So how do I write it? X minus y is what? What is it congruent to? Yes, which is also equivalent to what? What is it congruent to? It's congruent to its own remainder. What's the remainder?
B?
No, look at it, that line right above the theorem. What's the remainder? Right here. It's 0. The remainder is 0. Okay, so that's what divisibility by n is. So it is in fact congruent to 0 mod n. Right? And now you can see if we just, it's the same if you like it's corollary. You can see what has happened algebraically. We subtracted y from the equation. So y was on the right hand side. I subtracted y from both sides, and nothing has happened. So it's as if that mod n isn't there. Okay, so but it is. So it turns out that such an operation as subtraction is still legitimate for modular arithmetic to begin with. So that's the first observation that takes us in that direction towards complete algebra. So that's subtraction, but stop there? We really are concerned more with addition, right? So remember that we have to demonstrate that. Well, actually, number one, to demonstrate before we do actual algebra, remember that we needed to demonstrate that our equivalence, not our addition on our set of equivalence classes makes sense. And fortunately, it already does. How do we know it? It follows directly from the remainder theorem. Okay, so because every number has a remainder, so when you carry out the operation, you have another integer, and it also has a remainder. So that's all, mod n. Okay, so that part works out the same, exact same way. So in other words, we got to proceed before we were going to use this corollary, but really let's remind us what's that we're talking about. So x is z sub n. I didn't say what z sub n is. Is the set of all equivalence classes under this equivalence relation. So technically, we have not defined the operations yet, but we already have a set. So we add operations, and then we verify the axioms, and we'll know it's a group. Okay, so we'll just continue tomorrow.